Yeah, welcome back. All right, we're going to talk about the chain rule today. So, what's the chain rule all about? So, let's think about this. Right now, if I was to ask you, hey, what's the derivative of sine x, you'd be able to do it, right? And you have it memorized. The derivative of sine x, it's just cosine x. We actually derived that with the definition of the derivative, but for now, we have it memorized. And if I was to ask you separately, what's the derivative of x squared minus 4? Right? You'd be able to tell me that too. The derivative of a difference is the difference of the derivatives. You're going to get the derivative of x squared is 2x to the 1. The derivative of 4 is 0, and so you just get 2x here. But not very exciting. But what if I was to ask you about finding the derivative of sine of x squared minus 4? So that is a composition of basically these two functions, where the innermost function is x squared minus 4, and the outer function is sine of x, or sine of stuff. We can think of it that way. Well, it turns out if you want to take the derivative of a composite, you must use this rule called the chain rule. Back in the day, I used to go into great detail of kind of deriving the chain rule, but I'm going to take a different approach today. I'm just going to basically tell you what it is, all right? And then we'll kind of backtrack a little bit to maybe make some sense of it. So here we go. What does this say? If you have the composite function f of g of x, right? If that's the function you have, otherwise known as f of g of x, otherwise written actually that way. If I want to take the derivative of that, it turns out this is what you do. So now how do you make sense of this? It looks like we're taking the derivative of the outside function, right? That's why you see f prime, but you're evaluating it at the inside function. So you're not changing the inside function. But then you're going to multiply all of that by the derivative of the inside function. This is the definition of the chain rule. You are going to want to memorize this definition. Now, believe it or not, it can also be seen in Leibniz notation, dy dx notation. And it looks completely different, but it means the same thing. And this one lends itself to talking about rates of change, right? So let's, for example, say y changes 2 times as fast as x. So maybe dy, not x, u. So y changes 2 times as fast as u. So dy du, say is 2. I'm just telling you that. I'm giving you that. And then maybe u changes 3 times as fast as x. So maybe that derivative is going to be 3. Remember, derivatives are rates of change. Well, if I was to ask you the question, how fast does y change as compared to x, you'd probably say 6 intuitively, right? And that is because rates of change multiply, right? If you're twice as fast as Johnny and Johnny is 3 times as fast as Susie, well, then you're going to be 6 times as fast as Susie, right? And that's kind of how that works. And I just made those names up. There's no real significance of those names. All right, so that kind of makes sense. Now, rather than getting into all the minutia of this, let's just get right after it. Let's do some problems and make sense. I'm going to do this first problem the long way, and then I'm going to do it the more direct way. So when I look at this, I have to view this as a composition. I have to see that my innermost function is x squared minus 4, right? So I'm going to let some other function u equal x squared minus 4. And then I'm going to take the derivative of that u with respect to x. Well, if I do that, I'm going to get 2x to the 1, right? If u is equal to x squared minus 4, then my outer function now can be represented, we'll call it y, right? Can be represented, hopefully you're saying, as the sine of u. Right? Think about it. If y equals sine u and u equals x squared minus 4, when I put these together, basically just substitute the u in, I would get this expression. Now, if I'm going to take the derivative of this, I would want to write it as the derivative of y with respect to u, because that's my variable right there. And the derivative of sine of u is just going to be cosine of u. Now, using that whole chain rule thing, right, dy dx, that's kind of what we're interested in here, right? It's going to be dy du times du dx. It's almost like you can think of the du's canceling. Now, dy du is going to be cosine of u, and du dx, that's just going to be 2x. So that's what my derivative would be. But if you look up here, there's no u's in that. We actually put the u's in that to see the composition. So you're like, if only I knew what u was equal to. Well, you do. U is equal to x squared minus 4. So you would get cosine of x squared minus 4 times 2x. You can see we are multiplying two derivatives here because we can express this as a composite of two functions. If you have a composite of three functions, you'd be multiplying three derivatives. If you had a composite of four functions, you'd be multiplying by four derivatives, and so on and so forth. So this is kind of like the long way to do the problem. And this is also to kind of show us that definition of the derivative that we saw up here, right? dy dx is equal to dy du times du dx. Now, I would never in a bazillion years do this problem that way, right? So how would I do this problem? All right, so hopefully you can follow me here. Sometimes it takes 2 or 3 problems before you get what I'm getting at. All right, so I'm going to rewrite this. So I have d dx, that just means take the derivative of sine of x squared minus 4. But this is what I'm going to do. When I see this composition, I'm going to view this as sine of stuff, right? So what is the derivative of sine of stuff? Well, watch how this works. The derivative of sine of x is cosine x. So then the derivative of sine of stuff would be cosine of stuff. Notice I'm writing the stuff. I'm not mutilating it. I'm not changing it. It'd be cosine of stuff, but then times the derivative of stuff. So in other words, times the derivative of that innermost function. And that would be my answer. And oh, by the way, that's what I got right there. Again, if you go back to the notation, it's the derivative, right? Cosine of stuff. So derivative of sine of stuff is cosine of stuff. It's the derivative evaluated at the stuff. The g of x, this is like your stuff right here. So the derivative evaluated at the stuff, and then this is times g prime of x. Well, that's going to be the derivative of stuff, okay? And that's the chain rule, and it'll always work that way. So you're like, I don't get what you just did. All right, well, let's do another one. So here we go. Find dy dx when y is equal to this. So this is what you have to do. You have to view this as stuff cubed, right? So you mean stuff cubed? Well, here's your innermost function. This is a bunch of stuff. It's a function of x. So I'm going to view this as stuff cubed. So now think about what goes on in my brain. I know that the derivative with respect to x of x cubed would simply be 3x squared. That's it. Well, then what would the derivative with respect to x be of stuff cubed, right? Where stuff is a function of x. Well, it would be 3 stuff to the 1. Notice it's the same thing as here. And so instead of x, I say stuff. But then because this is a function of x, I have to multiply by the derivative of that innermost function, by the derivative of stuff, okay? Another way I can view it in function notation, derivative with respect to x of, instead of saying stuff, I'll say g of x cubed, right? It would be 3 stuff, so 3g of x squared, and then times the derivative of stuff. All different ways to do it. You can apply the chain rule to any differentiation formula you know. So I'm going to take a little bit of a side here. I know this is the problem at hand, but I'm just going to mess around and be like, oh, what do you mean? So like, for example, I know the derivative of ln of x, that's just 1 over x. Okay, so how do I apply the chain rule to that? Well, now think of it as the derivative of ln of stuff, right? Well, then, okay, wherever I saw the x, I say stuff. So it'd be 1 over stuff, but then you just have to know since stuff is a function of x, you multiply by the derivative of stuff. So this is using an existing rule that we know and just what I like to call applying the chain rule to it, okay? So again, it's going to take a little bit before you get it, but trust me, you'll get it. So all right, let's go back to the problem at hand. So how do you view this? And I'm even going to write this because I'm going to ask you all the time, how do you view this? And you'd say, oh, I view it as stuff cubed. So then the derivative is going to be 3 stuff. Do not mutilate stuff, right? See this? It's exactly the same. Don't mutilate the innermost function. So it's 3 stuff, let's subtract 1 from there, squared, and then times, and this is where the chain rule actually comes into play. Think of chain as just multiplying a long chain here, times the derivative of stuff. Well, stuff is x squared plus 5x. Derivative sum of the derivatives. The derivative of that is 2x to the 1 plus 5. This would be wrong because it's times all of that. That's a binomial. And that's it. That's basically it. Now, listen, sometimes you're going to be able to spruce these up. There's not much sprucing you can do here. right? If you want to rearrange this as 3, 2x plus 5 times x squared plus 5x quantity squared, knock yourself out, but that's it. This is your slope producing machine or your instantaneous rate of change producing machine on the graph of y at any point x, and we're doing it using the chain rule. One more generalization before we get going into the next problem, right? And again, this has nothing to do with this problem here, right? Only this stuff above. What if you're like, oh, wait a minute, so hold on a second. So I know, because you told me to memorize, that the derivative of radical x is 1 over 2 radical x, right? I told you to memorize that one. So then what would the derivative of radical stuff be? So radical stuff, what's the derivative of that going to be? Well, hopefully you're saying 1 over 2 radical stuff times the derivative of stuff. Maybe I'll call that stuff prime. Okay? That's it. Now, the mathy people don't use the word stuff. They like to use u. So they'll say the derivative with respect to x of radical u, so maybe I'll do this over here. Derivative with respect to x of radical u, where u is a function of x, what's that going to be? Well, it's going to be 1 over 2 radical u and times the derivative of u. And since u is a function of x, it'd be times du dx. That's a more fancy way of saying what I'm saying over here. All right, let's keep going. Trust me, it will make sense. All right, 3, find df dx, where f of x is equal to this stuff. So on this particular problem, if you're going to take the derivative right now, you'd have to go ahead and use the quotient rule because you have a quotient. But I would argue that since the top is a constant, it might behoove you to first rewrite f, right? We know that's a huge skill to have when you're taking derivatives. So rewrite this as negative 7 and then 3x plus 5 to the negative 2, right? Nice and easy like that. But now I want to take the derivative of that. So how do I view this? Well, I have a constant, right, times a function. So I know that the derivative of a constant times a function, right, f prime of x, is simply going to be the constant times the derivative of the function. So now when I get to the function part, this, I would ask you, hey, that's not just like sine x, or it's not just x squared. That's a composition. That's a bunch of stuff to the negative 2 power. So in your brain, you're like, well, hang on a second. If it was just a derivative with respect to x of x to the negative 2, it's not that. But if it was, the power rule would just say that that's negative 2x to the negative 3, right? So you're like, all right, but it's not x, it's stuff. All right, no big deal. Replace the x with stuff and then times the derivative of stuff. So here we go. The derivative of stuff to the negative 2. It's negative 2 stuff. Don't mutilate stuff, guys. To the negative 3. That's where this structure comes from. But then the chain rule says multiply by the derivative of stuff. In other words, multiply by the derivative of the innermost function. The derivative of 3x plus 5, it's just 3. And that's what you get. And now you can spruce this up a little bit here, right? Let's think about this. You got a negative times a negative. That's going to be 14. 14 times 3 is going to be, 30 and 12. So 42. And then 3x plus 5 to the negative 3. Now, if it's a multiple choice, you may not see this. If it's free response, leave it. If it's a multiple choice, what might you see? You might see 42 over 3x plus 5 quantity cubed, just using property of negative exponents there. Again, this is the slope producing machine for the graph of f. All right? Hopefully it's starting to make a little bit of sense. It's one of those things that you just have to practice, practice, practice. All right, so now let's kind of throw a little wrinkle in the mix here where we give you some graphs to probably answer the same types of questions. All right, so you got 3 functions here, and notice they're all compositions, right? So a of x, I'll rewrite it, is f of g of x, right? It says it right here. So they want you to find a prime of 1. So we've said this before. It's probably going to make sense for you to first find a prime of x, right? So you're like, all right, a prime of x. Well, how do I take the derivative of this? Well, this is a composition, right? So the way you do it, you view this as f of stuff. What is the derivative of f of stuff? Well, it's going to be f prime of stuff which is g of x, don't mutilate it, that's a horrible g, you get the idea, times what, guys? Pause the video, answer it. Times the derivative of stuff. Oh, by the way, this is what I told you to memorize. This is just basically the notational form of the chain rule. So you're like, all right, so now how do I do this? And I'll bring it back up here. You want to do a prime of 1. So just plug a 1 in where you see an x. So that's f prime of g of 1 times g prime of 1. And you got to kind of work from the inside out. So the first thing you're going to do is you're going to do g of 1. Well, how do I do g of 1? Well, I have the graph of g, for God's sakes, right? So here's g. G of 1 looks like that outputs 2. And you're like, all right, well, what about g prime of 1? You don't have the graph of g prime. You're right, I don't. But I know that g prime of 1 means the slope of the tangent line on the graph of g at 1. So here's 1. So what's the slope of this tangent line? Well, if I extend it long enough, I see we're going through here and we're going through here. So g prime of 1 looks like it's up 2 over 1. All right, so just a coinky dink, right, that it's going to be the same exact thing. So that's also going to be 2. So then you're like, well, what do you do now? All right, well, f prime of 2. Can I figure that out? Well, here's the graph of f. 2 is right here, right? So now f prime of 2 means the slope of that tangent line, right? And again, it looks like it goes through that point and that point. So that's going to be down 1, 2, 3 over 1. So that looks like that's negative 3. So I end up getting that my final answer here is going to be negative 6. What a solid little question, right? Testing you on all sorts of goodness. All right, so what's the next question here? I'm probably going to scroll down and then scroll back up. So we want b prime of 5. Okay, so all right, so what's the story here? Let's change the color up, maybe go back to black. Well, b of x is right here. So b of x is the composition g of f of x, right? It's not a product, guys. It's not saying g of x times f of x. It's g of f of x. So the first thing I would do is I would find b prime of x. So this is like, I view this as g of stuff. So the derivative of that would be g prime of stuff, don't mutilate stuff, times the derivative of stuff, times the derivative of that innermost function. That's just using the chain rule. It's exactly this, just yeah, g and f switched, no big deal. So the question said b prime of 5. So put a 5 in wherever you see an x. So g prime of f of 5 times f prime of 5, right? So again, you got to work inside out here. What's the deal? F of 5, here's the graph of f. 5 is right here. It looks like that y value is 2. So that's going to be 2. F prime of 5, right? What's the story with that? Well, that would be, did I just screw that up? I completely screwed that up. Thank God I caught it. I would have ruined my whole night. Right? Hopefully you caught it too. Hopefully you're like, what? What'd you just do? You're not making any sense. Right? F of 5, duh. I got to go on the F graph. That's the blue graph. So f of 5 is that value there, which is 1, 2, 3, negative 3. Silly me. All right. And then I have to do f prime of 5. That's the slope of the tangent line at 5, which if I extend this, it goes through that point, it goes through that point, looks like up 1 over 1, 2. So it looks like f prime of 5 is going to be a half. So now I got to rewrite what I have here, guys, right? F of 5 is negative 3. So this becomes g prime of negative 3 and then times a half. So what is g prime of negative 3? Well, let's see here. Go to the g graph, make sure I don't screw this up this time. Negative 3 is here. This is g prime of negative 3. Now I want g prime of negative 3. So it's really the slope of that tangent line, which looks like that's up 2 over 1. All right, so that's just going to be 2. So you're going to get 2 times a half. So you end up getting 1 here. So all that work just to get 1. Love when that happens. Okay, there you go. Rocking and rolling. Let's do the last one. So the last one now says c of negative 1. So I want to be able to see the graphs here. So maybe I'll squeeze this work in over here. All right. So c of negative 1. So first off, what is c of x? C of x is f of x. I'll do it down here. All right. So I'll remind us that c of x is f of x. So now c prime of x would be the derivative of the outer function evaluated at the inside stuff times the derivative of the inside function. So that's what you'd get. Looks a little weird, but it's just like the f's in the G one, just everyone's an f. So now if I want c prime of negative 1, that would be f prime of f of negative 1 times f prime of negative 1. So let's go do these. So first off, f of negative 1. Well, again, I got to go to negative 1. I got to go to my f graph. It looks like that f of negative 1 is 4. What about f prime of negative 1? Well, that would be the slope of that tangent line. And that looks like that's up 1 over 1. All right, so it looks like that's just going to be 1. So when I come down here, right, I'm going to get f prime of, we just said f of negative 1, that was the y value of 4. F prime of 1, that was the slope of the tangent line, which was just 1. So you end up getting this. So now you're like, all right, so now I got to do f prime of 4. So let me go back to the graph of f at 4. So here's 4, right? Slope of that tangent line. If I extend it, again, it's going through those points. We've already did this one. It's up 1 over 2. So it's going to be a half. So we end up getting a half times 1, which obviously is just a half. All right, so this is a great question because it's basically just driving home the notion of the chain rule. I don't want to say abstract, but it's kind of in an abstract sense. We don't actually know what the graphs of f and g are, so you got to kind of use that actual memorization formula that I said with the appropriate names there, right? If that makes sense. All right, so that's it for now. All right, you have homework. You should get after the homework. Do the homework first on your own, and then I'll make a video to go over it. But that is the chain rule, and it's probably the quickest I have ever gone over it.